Transformers are quickly coming for your favorite models. Yesterday they replaced LSTMs in NLP. They used to be good at NLP, but blah, we now have transformers. Think again. Today we're going to see that maybe in the near future transformers will replace convolutions in image processing. So this paper is a step towards this direction. You just wonder, what is it going to be tomorrow? Maybe linear regression is going to be replaced just by giant transformers trained on 5,000 TPUs. Who knows? We'll see. In any case, we're looking at Axial Deep Lab standalone axial attention for panoptic segmentation by Huiyu Wang, Yukun Chu, Bradley Green, Hartwig Adam, Alan Yuil, and Liangqie Chen of Johns Hopkins University and Google Research. So this paper combines a bunch of techniques that have been introduced recently to deal with attention in problems where you would traditionally use a convolution. So in this particular case, they deal with this problem of panoptic segmentation, which basically you'll get an image and there's a bunch of stuff on the image, like a cat here and a house right here, and you're supposed to color the pixels of the same object the same. So you see all these pixels here are house, and then all these pixels right here are cat, and so on. And then there's also the background, so all these pixels right here, I know, beautiful, 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 our background. So for this problem, it's kind of important that you're very precise, first of all, so you can look at pixels or clusters of pixels, and also that you take long-range dependencies into account. Because if you, for example, recognize that this is a house and you recognize that here's a wall right here, you might be able to much better classify what is wall over here and what isn't. Okay, so the kind of long-range dependencies play a role in these problems across images, and usually attention mechanisms are pretty good for these long-range dependencies, but they're also expensive, and that's what this paper deals with. So they use this axial attention that has been introduced for exactly resolving this problem in types of data like images or higher order tensors, and they also combine this together with learned positional encodings, which we've also seen time and time again throughout the kind of transformer and attention literature. So the combination of axial attention, these learned positional embeddings, allows them to replace the ResNet backbone that usually is found in panoptic segmentation models with a standalone attention. So they build models that are partial replace the convolutions with attention modules, or replace them entirely. So the entire model is going to be just an attention model, so no more convolutions in it. And they perform pretty well in classic tasks, like they test on ImageNet classification, they perform pretty well, and they achieve state-of-the-art on some of these segmentation tasks. So we'll go through the model right here. This is a very, very extensive paper in terms of experimental evaluation. What I want to get into is mainly how the method works and show you what their model looks like. So we'll go through it, and as always, let me know what you think in the comments and tell me if you liked it or not. Share it out if you did. All right, so they go over a very long list of prior work, which is, pretty cool. And here they say their contributions. So their contributions are fourfold. First of all, the proposed method is the first attempt to build standalone attention models with large or a global receptive field, and we'll see what that means. We propose position-sensitive attention layer that makes better use of positional information without adding much computational cost. We show that axial attention works well not only as a standalone model on image classification, but also as a backbone on panoptic segmentation, instance segmentation, and semantic segmentation. maybe what I described before was instance or semantic segmentation and not panoptic segmentation. Excuse me if that's the case. As you can see, it can be used for various image tasks. Lastly, our Axial Deep Lab improved significantly over bottom-up state-of-the-art on COCO, achieving comparable performance of two-stage methods. We also surpassed the previous state-of-the-art methods on mapillary vistas and cityscapes. So these are various tasks, as I said. And also what they don't mention here is that they perform fairly well on ImageNet. In fact, in the abstract, they formulate this as, in particular, our model outperforms all existing standalone self-attention models on ImageNet. Like that's, that's a way to phrase it. You just exclude all of the other models until you're the best. Outperforms all existing standalone self-attention models on ImageNet. Yeah, I mean, that's good. I mean, there's something to be said of comparing apples to apples, but you can also go overboard if you want to make your work look as good as possible. Of course, everyone does that, and there's no particular shame in it. Okay, so we're going to build up our model right here, and the basic element of this model is going to be this self-attention mechanism. Now, quickly, because I know you all know what it is, but very quickly, you want to perform this action right here over a region right here. So there is always a query. And now the subscripts here are going to be important in this paper, okay? So the query is at a given position O. And you can see that's the O right here. That's I'm going to call it the output. I guess that's what they said as well. So the output position. You want to go over all of the input positions, and you want to aggregate data from all of the input positions. So that's right here. And how do you aggregate data? By this softmax operator right here. And you can see the key also has a P right here, and the softmax is over the axis of P. So in particular case of the images, what does that mean? If you have an image right here, it's made into pixels, okay? So you have pixels. Now, a transformer, or in generally these attention models, what you can imagine is they always transform a data point into a data point of the same dimensions. Now, this doesn't have to be, actually, and I think one of the developments that is going to come in coming years or months or weeks, maybe someone's already doing it, is in fact to play more with this arbitrary constraint that we're imposing on ourselves, because it's not really clear that this is the best thing. But for now, an attention layer is always transforming a data point, here a 4x4 image, into a data point of the same size, also a 4x4 image right here. Now this is, as I said, this is quite simplified, but it is true in NLP, where we always transform our whatever 512 token sequence into a 512 token sequence, and it is true here. Now the output is going to be here on the right, and the question always is, okay, so I'll go over these pixels right here, and for every pixel, let's say for this pixel, I'm going to ask what data goes there. What's the output of the layer at that particular pixel? And the output of the layer is going to be somehow dependent on the input right here. Now, if you know classic convolutional models, what the classic convolutional model says, the output of this is going to be dependent on this region right here, if it's like a 3x3 filter, okay? So you have this convolutional filter, and that means that blue dot on the right is going to pay attention to, its own location in the input plus everything around it, okay? And then every single data point here is going to do that. So for example, this green data point is going to pay attention to this region right here. Now there's a border, so there's maybe some padding, but the question is always, where does the information come from and how is it aggregated, okay? In a convolution layer, what happens in a convolution layer? In a convolution layer, you simply have your filter, right? You have your filter, and the filter has numbers in it like 3 and 5 and 8 and so on. And what you're going to do is you're going to take this region right here, this blue region of the lower layer, and that's also, you know, filled with numbers like 7. What's a good number? 0 is a nice number, and you're going to multiply those, and then you're going to sum them up, and then you're going to put that on where the blue dot is. Okay, so where does the information come from in the convolution? From around the location, from around the output location, but in the input. Okay, so you go to the input at the same location as where you want the output to be. You take the neighborhood, and there is a fixed scheme of aggregating the neighborhood. Okay, and then you multiply and you sum across it. In contrast to this, in a fully attentional model, where does the information come from? Let's again look at the blue dot and let's consider it fully attentional. Okay, where does the information come from? Everywhere, anywhere at all. Okay, the information comes from everywhere. Now, how do I know how to aggregate the information? So it's no longer in a neighborhood. How do I know how to aggregate the information? That's also different. So two things are different. Now, in a convolution, I would have another 4x4 grid here that's pre-specified. But in the attention model, this here is basically all filled with question marks. Question mark, question mark. What number goes here? How do I in the end, I also do this multiply, and I sum it up, and I put it right here. Okay? But how do these numbers come to be? Well, these numbers also come, these are dynamically computed also from the input. It's a bit special, but this is how attention works, okay? So every pixel gets to decide where information comes from and how it is aggregated. It comes from anywhere, and how it is aggregated is dynamic depending on the pixel. If you still don't understand it, maybe pay out to watch a video on attention itself. I happen to have made one, but you can watch any one. When you understand that, you will understand the extension here to the image. It's the exact same thing as with the sequence, except the pixels are basically one long sequence in the image. Okay, so these would be a fully attentional model down here. Now, what's the problem here? The problem is that pictures are pretty large. So even something like MNIST, which is like 28 by 28, is like 700 pixels plus. I don't remember exactly, but it's like about 700 pixels. And our big transformers now, so BERT, a very famous transformer, takes inputs that are like 512 in length. And you already need pretty decent hardware to run this. And the requirements on memory and compute scale quadratically with the input length. So already with MNIST, you're in pretty shady territory. If you go up to something like ImageNet, which is like 225 by 225, that's bad, right? That's not good. So you have to come up with something else. So people have been playing around. The reason why I introduced it this way is people have been playing around a bit with sort of coming up with an intermediate, with a compromise between the two. So the compromise that this paper here focuses on is going to be a compromise where you remember when I said, where does the information for a given pixel come from? And we said, okay, it can come from anywhere in the attention framework. And that's good because that allows us to make super long range connections. So any pixel can aggregate information from any other pixel, and not even in a fixed way, but in a dynamic way. So depending on the pixel value itself and the other values, it can decide how it wants to aggregate information. That turns out to be expensive, right? Every pixel together with every pixel, well, that's quadratic. Okay, so what do? We make a third method that's going to be a compromise. And the compromise is going to be the following. The compromise is going to be, all right, we still do the dynamic aggregation, which means that we still do the attention thing. However, we're going to restrict back to this neighborhood region of the convolution. So in this model, where does information for the blue dot come from? It again comes from this neighborhood right here. And this number, the size here is going to be called m. So it still comes from that m by m neighborhood. So a pixel can only aggregate information from its neighbors, but contrary to a convolution, how it aggregates the information, like this, what in convolution would be a kernel, the kernel is made dynamically by the attention module. And it's made dynamically on a case-by-case basis. Okay, so we restrict it to a neighborhood, multiply, sum it up, and then put it into the output. And we do that for every pixel. Now it resembles much more a convolution. It's simply a convolution with this dynamic matrix right here. And that's the starting point for this paper. So this paper does two things to this. It says, okay, we can augment this by so-called positional embeddings. A positional embedding you might know from the sequence transformers. So if I have a sequence, my cat is tall. Don't even know what that means for a cat, but okay. What in a positional encoding, so if you use a transformer and you transform this, as we said, into a sequence of equal length, and then transformer is basically information routing. The transformer simply sees the lower layer sequence as a set, not as a sequence. It has no notion of what's neighboring to what comes from where. So it pays to tell the transformer, by the way, this is word 1, this is word 2, this is word 3, this is word 4. There are various ways to do it. Transformers usually have fairly complicated kind of sine wave based positional encodings that bring many advantages with them. In this case, they say, well, it might pay off to learn where actually these things are in this neighborhood. So they experiment with relative positional encoding, which means they annotate this neighborhood with something like, look, here in the middle, it's a 0, 0. Here it's like 0, 1. Here it's 0, negative 1, negative 1, 0, and so on. So they annotate it with these positional encodings. Now, this would be the easy way. What they actually do is they give the model a matrix like this, and they learn that matrix by heart, let's say. So the positional encodings are relative positional encodings, and they are learned. Okay, so you can do that. You can learn positional encodings. So if you don't want to do the 1, 2, 3, 4 right here, you simply say, well, here's a vector, here's a vector, here's a vector, and here's also a vector. Now, model, you're already learning like all the weights to make this thing here happen, and you're already learning your output weights up here, right, using backpropagation. Why don't you learn yourself what you would like for position 1, like what kind of information you would like to have there using backpropagation, right? So the model, you provide the model, you always provide the same vector. So this is the same vector for position 1, and you have a different vector for position 2, and you have a different vector for position 3, right? So, but across all of the data points, these vectors are going to be the same. So the vector 1 is always going to be that same vector for all of the data points. So the model somehow must learn independent of the data point what it means to be in position 1. So the model must learn how it wants to fill that vector. That's called a learned positional embeddings. We've seen this in many models so far. It usually works pretty well, and I guess here it works especially well if you have these relative positional encodings. And so this thing here is not going to be an actual matrix filled with these numbers. It's going to be a learned matrix, a trainable matrix that is filled, that the network is allowed to fill with numbers, right? Like 3, 5, 8, and you might notice that we've seen this before, right? So ultimately, the information in this blue thing right here is going to depend on this dynamically created aggregating of information through the neighborhood and this statically learned aggregation of information throughout the neighborhood, which is sort of a convolution, right? Because in the convolution, you've already seen here, this is a statically learned map of how to aggregate information from the neighborhood of a pixel. So I think, even though there are slight differences, they, for example, say these are the same across attention heads and so on. However, I suspect that you can think of these learned positional embeddings to be kind of like what you learn in a convolution. Not exactly. So no, I think I made a mistake, and we'll see it in the formula. Yeah. Okay. So here they introduce these positional embeddings. Okay, so you see that previously we had the softmax. Previously we had this and this. Okay, so this is the lower layer. This is the information that comes into the layer, and now it's transformed into values by a linear matrix. But essentially, this is the lower layer, and for each of the output locations, you want to know how should I aggregate information from that lower layer, and you do this by this thing here. This thing here is this dynamically constructed attention matrix using also the softmax. Okay, so how should you aggregate information? This comes from this query at the output position and the keys at the input position. And now you add to that this thing right here, which is again an inner product between the query and the positional encodings. Okay, so the positional encodings are going to be learned and hard-coded, but they still are modified by the queries. So the query can still pay attention. The difference is the keys depend on the input, while the positional encoding does not depend on the input. So the queries can decide, I want to gather information from this and this and this type of information. So that would be the key. Or it can decide, I would like very much to look at pixels that are somehow on the bottom right of the pixel that I am now. That would be the positional encodings. And that's the mistake I made when I said it's equivalent to a convolution. It is not, because the query it's still modulated by that query vector of how to aggregate information. Otherwise, you would have this to be a standalone multiplied by the input right here. But it sort of pays off to think of it like what you do in the convolution. So in the convolution, you learn how to aggregate information basically based on position, relative position to the position that you want to output. And here you do a similar thing. You learn static position embeddings that you then can attend to with your queries. All right, so these are the position embeddings, and they make use of those position embeddings. In fact, they attend them to the following. In this work, we enable the output to retrieve relative positions beside the content based on query key affinities, formally. So the problem up here is that, okay, you have these position embeddings, and here are the outputs. But if you do this in multiple layers, right? If you do, let's go with 1D sequences. If you do this in multiple layers, and here you annotate the position, let's just go 1, 2, 3, 4. And okay, this layer can make use of that, right? We gather stuff from here, but then when this layer gathers information from here, where the information comes from in the layer below is somehow getting lost, right? So it cannot kind of pull through this information to here, or at least it's very complicated. This model extends this positional embeddings in order to pull through that information. So as you can see, there are two new things right here. The important new thing is that right here, so here is how we aggregate information, okay? And here is the information that we aggregate over. Now you can see previously this was just this value vector. And now it is extended to the positional embeddings, learned positional embeddings. Okay, so with this you're able to route the positional embeddings to the output. And also here you can see the attention gets fairly complex. So you have query key attention, which is classic attention. The queries can attend to positional encodings, but also the keys can attend to positional encodings. So not only can the node on top say, I would like to attend to position 3, position 3 can also say, well, together with me, positions 2 and 4 are fairly important. I guess that's what that is. Maybe I'm mistaken here, but you can see right here there is an interaction between the keys and the positional encoding right here. Now these positional encodings, they are different for the queries, keys, and values, but ultimately that doesn't make too much of a difference. So here is a contrast between what a traditional attention layer would do and what they would do. So a traditional attention layer gets the input X and transforms it by means of these linear transformations right here into the queries. These are the queries, let's call them Q, into the keys and into the values. Okay. Then it does a matrix multiplication with the keys and the queries and puts that through a softmax. So this here is going to be our attention matrix. This is the attention matrix, and the attention matrix is multiplied here by the values, and that determines our output. Okay. Again, the attention matrix defines how we aggregate information, and the values is what information do we aggregate for the output. In contrast, when we introduce these positional encodings, you can see right here, again, we have query, key, and value. Now, it gets a little bit more complex right here. Namely, we do this query key multiplication right here, but we also multiply the query by these positional embeddings for Q. We also multiply the keys by the positional embeddings for K, and all of this together, so this is a big plus right here, all of this together is routed through the softmax. Okay, and now the diagram is a little bit complicated. Now you can see the softmax aggregates information from here and from this learned positional embeddings. I would rather they would just use it like they did in the formula, do V plus R and say that's going to be the information that we are aggregating, and the softmax here, the output of the softmax is going to be how we aggregate information. This is the attention. All right, I hope that's sort of clear. You introduce these positional embeddings for queries, keys, and values, and that allows the model to have a sense of where the information is coming from, basically what positions, which if you drop the convolutions, so the convolution had this intrinsically, because in your convolutional kernel, right, I'm dumb. If in your convolutional kernel, the number right here, if there was a 7 right here, that meant that wherever you are, whatever's on the bottom right is 7 important, okay? So that was the convolution had this intrinsically. Here, if you just do attention, we as humans, we see it in this kind of grid form, but the machine doesn't. The machine simply sees a set of pixels. It simply sees, this is to the attention mechanism, this is exactly the same as a long list of pixels or a discontinued set. It doesn't matter to the machine. So it's like the problems a feed-forward network has. So we need to annotate it. We have to give it positional information, and learned positional information seems to work very well right here. Though you could think of static positional information. Okay, this is the first thing, the positional embeddings that now help the attention mechanism see where the information is coming from. That's really important in pictures, so we add that. The second thing they do is this so-called axial attention. Now, axial attention is sort of a, let's say, a trick in order to reduce the load on an attention mechanism. So, what does it mean? We've already seen in sequences, right? If I have a sequence layer, that's going to be n squared connections between the two. Now, there are various ways to restrict that. So instead of having all of these connections, let's say from one node, we've already seen, wait, if we just restrict it to, let's say, only this thing right here, only this stuff, that is lower, right? That is lower in complexity. And this, in this case, it would be just a neighborhood. So that's what we've done. That's this M thing right here. However, we can also do it in different ways. Since this is a set anyway, we can simply say, maybe we should just always skip one. We could do attention like this. And that would be just fine too, right? That would also leave away some of the information, but you gain in computational efficiency. There are various trade-offs. Now, in a picture, you have the same options, right? So you can do the neighborhood thing as we did, or you can say, where should the green pixel pay attention to? Axial attention says the green pixel should pay attention to only the row where it is in. Okay? It should ignore the rest of the input. It should only pay attention to that row where it is in. And then in the next layer, we'll flip it. Then the green pixel, the same green pixel, will pay attention to only the column it is in. Okay? So that's called axial attention, but don't think, there is nothing special about this being an axis or whatnot. You could also define it would not be called axial attention, but you could define it makes the same sense to say, well, that green pixel, it just depends on this diagonal right here. It just in this layer, it just does this diagonal, and then in the next layer, it does like the anti-diagonal. You can say, I just choose 5 random pixels in this layer and 5 random pixels in the next layer, and that would work as well. We've already seen this in this paper called Big Bird, right? The Big Bird, but Big Bird. So Big Bird explicitly used random connections in the attention mechanism. And their argument was, well, if we use different random connections in each layer, then information can travel pretty fast through the network. So what's the problem with these neighborhoods right here? What's the problem with neighborhood attention like this? The problem is that you break the long-range dependencies. So let's see what happens if information needs to go from this pixel to this pixel, or this node to this node. Right? If information needs to travel from this node to this node in a classic attention mechanism, everything's connected to everything. So that node in the next layer can simply aggregate information from here. Well, that's not possible if you do this kind of neighborhood attention as we've done here. If I do neighborhood attention, then at most, right, because the neighborhood is 3 long, at most this node right here can aggregate information from this node. And then again, it's 3 long in the next step, so now this node can aggregate information from this node. Okay, because the neighborhood is 3 long, and you can only attend to within your neighborhood. This means that if I want to send information to something that's really far away, I need to go many layers, right? I need to go layer, and this has been well known. This has already been a problem. This has already been a property of convolutional neural networks. So convolutions specifically traded off the fully connectedness of fully connected layers to local connections, convolutions, but that means that you have to go very deep in order to make long-range connections. You can't just make them in one step. The same problem right here. Now, this paper, Big Bird, argued that if you have random connections instead of neighborhood connections, just the property of random graphs mean that you are pretty fast in sending information around. So because in a random graph of size n, on average, all 2 nodes are connected by path lengths of log n, this is much faster. Because in this neighborhood thing, 2 nodes are connected in a path length of order of n, right? You can pretty easily see that if I make the sequence longer, I need that many more steps in order to send it around. In fact, it's like something like n divided by m, this neighborhood size. In a random graph, it's log n, and in this axial attention, that's why I introduced it, it's 2, okay? Every 2 nodes are connected by 2 steps, okay? If this node right here needs to send information to this node right here, in a classic attention mechanism, it could do so in 1 step because every pixel attends to every other pixel. However, right now, we have to see. So this node attends in this layer. Sorry, I have to think. So how do we send information between the 2? We select this node right here. In the first layer, this node pays attention to this row, okay, which includes the red dot. So the red dot can send information to the X in this layer. In the next layer, we select this node right here, which is our target node where the information should go to. Right? It pays attention to all of this column, which includes that X that before, right? This X right here, where we send information to. So it takes 2 layers, 2 steps to send information from any node to any other node. Well, that's pretty good. So this axial attention, if you stack them on top of each other, you sacrifice a little bit of being able to send information from anywhere to anywhere for the pleasure of not having this quadratic attention anymore. As you can see, your attention mechanism is now as long or as big as your column or is wide or your row is high. Again, this isn't specific to rows or columns. You could do this, as I said, with these kind of diagonals. You could do it with any other sort of sub-pattern where you can sort of guarantee that the overlap between the layers is enough so you can send information around pretty efficiently. And they use this right here. So this axial attention, you can see the formula is exactly the same. The only change from before is this part right here. You can see that the neighborhood that they aggregate over is no longer m by m, it is now 1 by m. So we've seen them going from, if this is the full input image, and you wanna see where to attend, what this paper does is it says a convolutional neural network would be attending to some subpart, right? This is convolution. An attention mechanism, pure attention, would attend to everything, right? This is attention. Then what we are doing, sorry, that was a mistake. What other people were doing were reverting back this attention to a subpart, this kind of neighborhood attention, okay? But that was still, you still have m squared, you still have O of m squared because of the attention mechanism. Now what we are doing is we are going even lower. We're actually going 1 by m. Okay, this is with axial attention. So in general it's 1 by m, and then in the next layer we can go 1 by m in this direction and have that property. And because it's so cheap now, right, because it's now O of m to compute this, we might as well make m as long as the row itself, okay? So their last step is going to be to say, okay, we have 1 by m right here, and that's going to be the row itself. Now, you can see right here that they say axial attention reduces the complexity to HWM. This enables global receptive field, which is achieved by setting the span M directly to the whole input features. Optionally, one could also use a fixed M value in order to reduce memory footprint on huge feature maps, which is something that they're going to do later on ImageNet, I believe. So when they have big inputs or big outputs, they actually do use a smaller M. What you can see right here is that that wasn't really correct of me to say that it's now O of m, because you still have the entire query space. So you multiply query by keys. Now, even if you make the keys to be 1 by m, yes, you reduce this from height times width to times height times width to this. But then you can see on this thing right here, if you take it and let's say we have this kind of row pattern and we replace m by the width, then we have width squared. So again, the square appears. However, it's smaller than the original attention. The original attention was h squared w squared, right? Because hw is the image and you need that squared in order to do the attention mechanism. Now we've basically reduced one of the factors. It is still an attention mechanism. So there's still attention going, but we've basically transformed the image, we've reduced it to one column. Now the one column is still attention. So this is still attention like here. So this now reduces to the attention that you see in a single sequence. Okay? If you see the image as a long stretch of pixels, what this does is basically it simply subdivides that into neighborhoods. So we're back to neighborhoods basically, but we shift the neighborhoods from layer to layer. So in the next layer, the neighborhoods are going to be just alternating, right? The neighborhoods is going to be, this is one neighborhood connected to this neighborhood, connected to this neighborhood. I hope this makes sense. So it's going to be, it's basically a mix between, if you were to do this in convolution, you could do one layer where it's neighborhood convolution, and then one layer where it's like convolution with holes in it. I think they're called Atlas convolutions or something like this, with like giant holes in it, that are exactly the anti-pattern of the neighborhood convolution from before. That's what this is. So you see their axial attention block right here. Their axial attention block replaces the ResNet block. So if you know ResNet, I've done a paper on ResNet. ResNet basically takes the input, pipes it through straight, and adds to it whatever comes out of this operation. Okay, that's a residual block. Now, usually this thing here would be convolutions and convolutions, and they are now replaced by these multi-head axial attention. You can see there is a multi-head attention in the height, and there is a multi-head attention in the width. And that gives us the property that every node can send around information to every other node in 2 steps. I don't like the fact that there is only 2, because I guess this gives a significant bias to one or the other direction depending on the order that you do them in. If I had done this, I maybe would have used 3 of them, because it depends on how you want to aggregate information, right? Like here, you train the network specifically to aggregate information first in this direction and then in this direction, which might work, and it'll give you that sending around information anywhere. So maybe they've actually tried and it just performed the same. So I just might have a dumb suggestion right here. In any case, they simply replace we've come a long way, right? We've gone to like neighborhoods and blah, 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 blah. Ultimately, take a ResNet, replace the convolutions with the height axis attention and the width axis attention, and we're good. And then we come to results. So that's it. You have these positional embeddings, you have the axial attention, and it turns out that on ImageNet, they perform fairly well. So you can see that models like a ResNet 50 model will get a 76.9 on ImageNet, which is not state of the art, but it's also not bad, right? The ResNet 50 is pretty good model. You can see the full axial attention right here achieves a 78.1, also not state of the art, but still pretty good. And as they say, it's the best fully attentional model on ImageNet, or standalone attention model on ImageNet. So where this model really shines is where you really have to make long-range connections between pixels, and that's these kind of segmentation tasks. And I want to skip the tables right here, they're best in everything, and go to the appendix where they have some examples of this. So here you can see specifically, this is the original image. You have a ground truth, and you have the differences between their model, this Axial Deep Lab, and the Panoptic Deep Lab. That is a baseline for them. And you can see that the failure cases here are pretty, show how the Axial Deep Lab is better. I don't know if they are cherry picked or not, but at least you can see that at some point, so it handles occlusions better, it handles instances better. So here you see that the ground truth separates the person from the tie, and the axial attention is able to do this, but the baseline is not able to do this correctly because it labels part of that white shirt also as, and you can see why. There's kind of a delimiter line here. But if you have long-range dependencies, right? If you have long-range dependencies in the model will recognize, wait, that must be the same thing as this thing here, and this thing here, and this thing here. So that must be the same object. It's simply that the shirt was occluded by the tie and goes beneath it and now appears again. It's not part of the tie, and it's not part of the of a different object. It's actually part of the shirt. So the long range attention, you can see at these examples sometimes here, okay, this might not be an instance of super duper long range dependencies. This is simply where the model performs better. So you can see here the ground truth has that surfboard segmented and the baseline does not. that this can also just be, there are a lot of tricks to make this work, of course, and you throw a lot of compute at it, and sometimes you just get better numbers or part of the better numbers because of the additional compute. Right here, what do we have? So you can see occlusions. It appears to handle occlusions in a better way, and this might be due to this axial attention. It might be due to the positional embeddings, but you can see that the ground truth here has the laptop between the person's hands segmented. The baseline cannot do that, but the axial attention does do that. And I don't know what this is. Honestly, this is you can see though the axial attention also misses the fact that it should segment this in the background. And if this occlusion handling, you can see best in this example where the person in the back reappears on both sides of that person. So you can see that the axial attention manages to segment that, where that is just a mutant person right here. The ground truth is equally shaky. I think might be some ambiguity of how you can segment these images, obviously. But you can see the fact that there are long-range dependencies probably helped with this, saying that, wait, in this image, there's this white stuff right here, and there's this white stuff right here, and connecting these two regions with attention probably helped in segmenting these to be the same object, even though you can see there is a break in the object. So there is a break. At no point is the object on the left touching, or the segment on the left touching the segment on the right, and still the model manages to put those into the same label category. There is the last thing where they want to research what their heads learn, and usually you can do this, right? You can kind of visualize what the attention heads learn. So in this case right here, in the column heads, the way you have to read this is that this particular head right here aggregates information from its column. So everywhere where it lights up, there's a lot of information being routed. You can see specifically in this here, the heads of the people, or the heads of the persons in the picture, light up fairly well. So for example, this head right here is probably aggregating information a lot from this position right here, and this head here is aggregating information from this position. So you can deduce that that particular attention head probably deals with people's faces, whereas that particular attention head probably deals, you can see the attention is mostly on the grass right here, and you can see the same with for the row heads. Now their description here is that we notice that column head 1 corresponds to human heads, while column head 4 correlates with the field only, which, you can interpret it as this. This seemed pretty clear. But then they say something like row head 6 focuses on relatively local regions, where column head 5 pools all over the image. So row head 6, which is this thing right here, you can see that, okay, it maybe focuses on small regions, though you can see, okay, like here you can get it, that's a person, but in other places, I don't know, where column head 5 pools over the whole image. And this, I don't know, maybe they just needed something more to say because they put these pictures here. They were like, okay, the column heads are really nice because we could, like, this one's really nice because it, just pays attention to the people, and this one looks really nice because it pays attention to the field. But we can't really put the column head attention without putting the row head attention. But then none of the row heads really are like super distinctive on a particular thing in the image. So we need to come up with something that we can say, and then you're like, there's not a lot of attention, so we need to contrast this with something. Then you would think that they contrast it with another row head, but then there's no row head that does this whole image. So there's like, column head 5. Yeah, I'm not sure if there's a bit of tactical writing going on here, I suspect. I mean, it's still, it's doing something cool, but yeah, there's definitely an element of sales in when you write research papers. And just not to this data, but just props to the lines in front of the histograms makes it so much easier to read how big the stupid bars are. Why does everyone put the lines behind the histogram? I probably do that myself, and now I'm realizing how much easier that is. All right, there is a big experimental section right here, and there's a big appendix where you can read up all of the different numbers, comparisons, ablations, whatnot. Ultimately, I just wanted to go over the method, basically putting this into context with other things, like putting this into context with stuff like Big Bird, axial attention, other positional encodings, how it relates to convolutions, how it relates to feed-forward networks, and what convolutions did to feed-forward networks, and so on. I hope you at least a little bit gained an understanding of what's going on here. And with that said, I see you next time. Bye-bye.